Okay, so thank you very much for the introduction, and thank you to the organizers for the opportunity to visit this beautiful place. I'm going to talk about mostly theoretical work, but at the end some experiments, work in collaboration with Benjamin Lev's group in Stanford about how to use their experimental setup, which is cold atoms in a multimode optical cavity, in order to study the physics of associative memory and spin classes. And I'll start with an introduction to what it is that I'm really going to try and talk about. I want to be able to use cold atoms and optical cavities to study models like this kind of thing here, a model of spins interacting via some connectivity matrix, Jij, with the idea that among many things you can realize an associative memory. And this cartoon down here is a cartoon of what an associative memory should do. The idea is that it should be able to store patterns so that if you put in a corrupted version of a pattern, then the dynamics of the system will naturally take you to the correct version of that pattern. And that idea of completing a memory is the same as also being able to put in something and look up an answer, because you could think of the complete memory as being the pattern plus an answer that's associated with that. So you can also think of that as a way to do database lookup. So there is a lot of literature about how you can realize models of spins which will have dynamics which naturally take you to the minimum of some effective landscape, how you can train that landscape to particular patterns. And the question that I want to discuss here is about doing that with a physical system which is clouds of cold atoms. So here these BECs placed at particular positions in a multi-mode optical cavity. So this cavity supports multiple optical modes. And to do this in the setup that's been done with many experiments for cold atoms and optical cavities, of having a transverse pump, so here the light that's in pink, transverse to the cavity, that produces a effective Raman transition between two low-lying levels of the atomic system. And that idea is very powerful because that allows you to attune more or less everything in the Hamiltonian of light coupled to matter. So this is the effective kind of model we're looking at. It's got many cavity modes, and most of this talk I'm going to consider the case where those modes are in fact fully degenerate, so that it's a truly multi-mode cavity. It has effective spins, which can either be two-level systems for a single atom, or for much of this talk I'll be talking about cases where it's a collective spin of many atoms. And then there is coupling between the light and the matter. And the basic question is, how do you use this physical system to realize this ideal model? And the basic answer to that is that we will use the individual clumps of atoms, the individual BECs, as the spins in this model. We will use the cavity modes as something which can produce a connectivity matrix. So the connectivity matrix will come from the cavity-mediated interactions. And the dynamics of this system that we will look at will be the dynamics of the open quantum system, accounting for cavity loss, etc. And we'll find that that can indeed recover the ground state of an effective connectivity matrix. And I should note that in all of what I'm going to say, I'm focusing on what happens in or at the boundary to the superradiant state of this kind of model. So this kind of Hamiltonian has a phase transition when this pump strength down here, when this effective light-matter coupling becomes large enough, to a state where there is light in the cavity and polarization of the atoms. And at least in the first part of the talk, everything I'm going to say is about what happens in that state. So that's the basic outline of what I want to talk about. I'm going to really tell you three stories about this, which will get increasingly fast and possibly even faster than I want if I run out of time. The first story will be purely theoretical so far about the classical dynamics of this model above the superradiant threshold. And I'll tell quite a bit of detail about that, of what the connectivity matrix looks like, what consequences that has for the behavior of this model, what the dynamics of this system look like, and how that can recover memories. Then I will tell you a much shorter story about more recent work, again theoretical, looking about the quantum dynamics near the threshold of this model. And then I will finally, at the end, talk about some very recent experimental work which has directly observed replica symmetry breaking in the spin glass limit of this model, in the case with relatively many atoms per clump. But I'll say more about that when I get there. So starting with this first case of looking far above threshold, what I want to focus on first is what is the effective connectivity matrix of this cavity-mediated interaction. And I wrote down before this kind of generic form of saying what I should do is sum over the mode functions of the different modes in the cavity, evaluated at the positions of the atoms. And so this gives a connectivity matrix Jij between clumps of atoms at position I and at position J, dependent on the set of all modes in the cavity. And in general, it depends on the detunings of the modes, but in everything that follows, I'm going to assume all the modes are degenerate. And in that limit, in the limit where all the modes are degenerate, but you deal with the realistic, or the real properties of the modes in a confocal cavity, including how different transverse modes are slightly phase shifted in a real confocal cavity, what you find is that you can in fact sum all of these modes and get a closed form expression, which has got two parts. It's got a part you might have expected when I sum a complete set of modes. I get a delta function that says there's interaction between atoms at the same point in space. And then you get another part which comes about because modes are successively phase shifted by pi by 2 as you go through the set of modes that are resonant in the multimode cavity, in the confocal cavity. And that phase shift has the effect of adding an extra term to this, which takes this form of cosine Ri dot Rj. And all that I'm going to say in the following is really relying on what is the physics of this cosine Ri dot Rj term. And this is potentially interesting because as you make the positions further and further apart, this thing will wind faster and faster and so will become effectively random. And you can indeed see this if I put atoms in at random positions when they are fairly closely spaced compared to this W0, which is the beam waste of a T00 mode, then most of the interactions are positive, cosine is positive, and if you look at this kind of all-to-all connectivity picture, all the interactions are positive. This is a ferromagnet. If you start to scatter them a bit further apart, then you start to see some interactions become negative, and when you scatter them even further apart, you see something where it's roughly equally probable to get a positive interaction or a negative interaction. And so you can then start to say in this regime you'll have frustrated links. There will be some links between sites which will be positive, some links will be negative, and this might mean that you can have more than one stable fixed point of this spin model, which is what you want for an associative memory. You want there to be multiple memories it could recover. But you might also then wonder, well, does this become a purely glassy system? And if Jijs were purely random, then you would start to get a purely a spin glass behavior. And you can start to ask questions about, are these Jijs truly random, by asking questions such as, if I take Jij and Jjk with one site overlapping, are these matrices independent? And this, in fact, you can calculate analytically for this cosine interaction, and you find that this does fall off as you increase this distribution, so this starts to look more random. I will say later on that actually this width becoming 3 isn't quite enough for this to be truly random, but it will eventually become random at large enough widths. So we have this Jij, which has a ferromagnetic state. It has this possibility to introduce frustrated links, and then eventually a transition to a pretty much random state. And so the question you can start to ask here is, well, with that connectivity matrix, what can I say about the metastable states of this problem? If I minimize the energy, find how many minima there are, what happens as I increase the width of this distribution? And what you're seeing on this picture is that, as you would kind of guess from a previous slide, as you increase this width, you start to get more and more local minima of this, this connectivity matrix, and so this does start to behave as an associative memory. What I've also shown here is the different lines are for different numbers of clumps, and this behavior seems to look that it's dependent both on this width and on the number of clumps. But in fact, if you look further and you rescale this, you find there is a rescaling dependent on system size, so that all of these lines collapse. And what this says is there is therefore effectively a critical width that is apparently 0.67 W0. We only know this numerically, at which there is a transition from a ferromagnetic state to an associative memory state. And at least over this range here, this data is very well fit by this formula, which suggests there is a system size dependent width of how sharp this transition is. So, is it? Yep. Yep.
Yes, there is something I don't understand about this associative memory. So I assume you want many minima, but
yep.
Then I still need to retrieve.
Yes.
So then if it becomes classy, I imagine that's pretty high.
Yes, I will come on to exactly that point when I talk about the dynamics, because it turns out that the answer to that question depends not only on the connectivity, but also on the dynamics, because different dynamics can make the answer to the question you're asking different. So can I come back to your question when I get to the end of the dynamics section? Okay? Yep.
And just to make sure, here we're thinking of S as kind of like a discrete or a continuous?
S is discrete, and here it's also it's all classical. This is just a classical number.
So to say it's a minimum, I would have to be able to flip any one spin and the energy.
Exactly. Yes.
No, just maybe a comment on that. If I remember correctly, the associative memory behavior is not the regime of spin glass. These are two different.
They are, but actually there was a subtle answer, but I will come on to at the end of the dynamics section. Okay. So, I mean, if you take the standard dynamics of a spin of associative memory model, so you take Hopfield dynamics, then sorry, let me forget that and start at a different place. So, one way of categorizing whether this is in a spin glass regime or not is just to ask about how many minima there are for this problem. I will come on to another point about associative memory later. If you focus just on how many minima there are, at least in textbook spin glass models, you would typically expect exponentially many minima with the system size. The analytic formula I showed on the previous slide, which fits near that transition to associative memory, is not exponential, but exponential, stretched exponential. So there is something subtly different going on. And so one way you can ask about where the transition to a spin glass on this is, at which point does this model look like the behavior of truly random JIJs? One way to do that is to compare this JIJ matrix to a truly random matrix. And so we did that, and we looked at the eigenvalue spectrum of a matrix or the level spacing statistics. Both of these show basically the same point, which is when the width becomes large enough, then this starts to match to the behavior of a random matrix. And here it seems that actually the width of 3, which was where things seem to become uncorrelated, that's not yet enough. And the point there is, while there's not strong pairwise correlations, there are still some correlations which only truly get washed out at a larger value of W. You can make this a bit more quantitative by saying, let me measure the difference between the distribution of eigenvalues for this matrix and the distribution of eigenvalues for a random matrix. And if you do that, then you get this kind of graph. Sorry, I've gone too many. Yeah, this kind of graph down here of how does that measure vary as you increase the width. The set of lines here again for different system sizes. Again, it looks like it's system size dependent, but once again, with appropriate rescaling, you find there is a kind of universal curve of how the overlap between the distributions varies as a function of the width. And that suggests, again, there is some kind of critical width, which in the large system size limit becomes sharp, at which point you get a transition to something with exponentially many minima. And what is notable here is that while the transition from the ferromagnet to the associative memory was at a critical value of W that did not depend on system size, this transition to where this looks like a Sherrington-Kirkpatrick model is system size dependent. So there is this kind of line here that says that you need W to the power 4 to be much larger than N, and then you get exponentially many minima. So this is half the answer to when do you transition to a spin glass, but the other half of the answer requires to think about the dynamics. And that's what I'm going to talk about next. So I said what we wanted to think about was the open system dynamics of this model. And in principle, this is a difficult problem because I've got many spins and not just many, but infinitely many cavity modes. There's a continuum of infinitely many modes that we summed up. So we need some trick to approach this kind of problem. This is why in this first work we focused on what happens far above threshold, because in this regime we can do various things. We are going to focus on trying to eliminate the dynamics of the cavity modes, but to focus on doing that far above threshold, where I can say that this light matter coupling is strong compared to this term omega naught. And if you treat this term omega naught perturbatively, the rest of the problem is something you can solve exactly. It's the independent boson model. You can find all the eigenstates of this, and then you can deal with this last bit in perturbation theory. And the net result of that is something well known in open system literature, that what you get is a rate of spin flips of the process that is described by this light matter coupling. So rate of spin flips described by this omega naught term. So these are things which flip the SX spin from along plus X to along minus X or vice versa. And the rates of these can be calculated from the mode structure and so on. So what you find from this is that there is this spin flip rate, which is large when you're on resonance with the cavity modes and falls away from this. And what you find more importantly is if you calculate the rate of a spin flip that increases energy versus one which decreases energy, so the rate of the forward flip and the backward flip, this ratio of rates fits reasonably well to a Boltzmann distribution, at least for low spin flip energies, and you can extract that there's an effective temperature from this. So this dynamics looks quasi-thermal, and what you find from that, which causes a slight problem, is that in this regime far above threshold, this effective temperature is relatively large compared to the Jij matrix, so you wouldn't necessarily go to the ground state, but you can fix that by making the size of the collective spins large, and then that will amplify the energy cost of having an unaligned spin, and so this will then produce something close to the ground state. What you also find in that regime is if you make the relative size of the spins large, this dynamics becomes very deterministic. So we actually simulated this in a stochastic way, that's for the solid lines here. But what you find is that in the limit of large spins, the real dynamics that occurs is whichever spin is most unaligned to its local field will flip first, and the flipping dynamics of that spin will be superradiant in the sense we heard about this morning of the original Dickey superradiance, the irreversible process. So you get dynamics which you can write down analytically that says there is this fast superradiant dynamics of individual spins, and whichever spin is most unaligned will flip first, and therefore it becomes a deterministic process. And this fact is what then actually starts to affect the question of glassiness versus associative memory, because the question you really care about for associative memory is as Anna said, not just that there should be a local minima, but that it should be stable, that you should be able to recover that minima from different initial conditions. And so a question you can ask is, how stable are these minima? Put in a state, slightly distort it, and say, do you get back to the state you want? And what this graph is showing is how likely you are to recover the state that you want, depending on the size of error. And it's showing this for two different kinds of dynamics. On the left, the red one, this is the thing which is often done in spin glasses of zero temperature metropolis Hastings. So everything which goes downhill in energy you do, and anything which goes uphill you do according to a Boltzmann distribution. Whereas the blue and the orange curves are showing either the exact dynamics of the cavity-mediated process or the steepest descent dynamics, i.e. flip whichever spin is most unaligned, and so on. And what this is showing is that this second case is much more stable to errors. And you can kind of understand that because if you say, well, if you go deterministically downhill, then you're never going to go accidentally uphill and escape from one local minima and go to a different solution. Whereas if you just randomly pick a spin and say, well, shall I flip this spin or not, sometimes you can go uphill and escape a local minima. And so this is what's kind of going wrong in the zero temperature metropolis Hastings case, that sometimes you can escape from one minima that you wouldn't have done with deterministic dynamics. So a net result of that is if I go back to a kind of standard spin glass connectivity matrix of just trying to store more and more patterns, with the zero temperature metropolis Hastings, the red picture, what you find is that above a critical number of patterns, you forget everything. And that's a typical behavior of a spin glass, or transition to a spin glass, that when you put too many patterns in, all of the basins of attraction collapse down to vanishing size. But with this alternate dynamics, with this steepest descent dynamics, you instead find that actually there is still some finite basin size. So this does not completely collapse. So this is why I said in answer to the earlier question, the dynamics actually matters for how robust things are. Did I answer your earlier question? Good. Okay. Yep. Oh, a few minutes. Okay. So the next few bits are going to be very fast. Actually, so I think I'm going to skip completely the theory of the system near threshold and just jump so I can talk about the experiment in the last 3 minutes. So what the experiment that's been realized by Benjamin Lev's group has done is to look at this kind of setup, so atoms in a multimode cavity, looking in the spin glass regime. So looking in a regime where we've made the atoms far enough apart that this cosine Ri dot Rj is effectively random. It's a slightly more complicated model than the one I showed before, in that it's not just got an SX-SX coupling, but there's also an SX-SY type, SY-SY type coupling. This is kind of due to complications of how the experiment was realized. What I should note with this is not an XY model. It's not a model with continuous symmetry. There's a minus sign in the middle here, so this is still a model with discrete symmetry. However, it does have this vector order parameter, so it has both x and y components of the order parameter. And the thing that's been done with this experiment is to just run the experiment, sweep through thresholds, so go into the superradiant state and find what configuration the system orders in and then study that directly. So if you work in a regime which is ferromagnetic, if you put the atoms in particular positions so that all the couplings are the same sign, then what you find is that indeed you can measure the phases of all the clumps and you find they're all the same sign. On this picture down here, this is showing that the magnetization is aligned along the x direction in this case. This is measuring different components of the overlap distribution between different replicas. So when you run the experiment many times, how similar is one pattern to another? Because of the vector order parameter, you can also say what happens if I change all the signs of interaction from positive to negative. In this case, it doesn't become an antiferromagnet, but instead becomes a ferromagnet along the y direction. But then the more interesting question is what happens if I do this where this really is a spin glass, so where all the JIJs are effectively random. And these 4 pictures here, what these are showing is 4 different runs of the experiment in that parameter regime, where each run gets a different solution. And then what's being shown down here is from running that many, many times, you can build up experimentally the distribution of overlaps between different replicas. So this is a direct experimental probe of the replica distribution and therefore a direct experimental probe of replica symmetry breaking. So this picture down here is kind of the thing you would directly want to see in an experiment to see replica symmetry breaking. It's the probability distribution of getting a particular overlap between 2 replicas in the experiment. What you can also do directly from the experiment is you can measure the properties of all of those replicas, how similar two replicas are to each other, and you can directly test ideas that have been theoretical ideas in the spin glass literature, such as ultrametricity, from this experimental probe. I should then point out this picture here is all for one particular realization of the experiment. You can do this again with a different Jij matrix, so different positions of the atoms and therefore different connectivity, and you can then look at it. In each case you get different overlap distributions, and you can average over disorder from that. Okay, so I should finish there. I should acknowledge the people involved in this work, in particular Benjamin Lev's group. On the left here, you see Brendan Marsh, who is the student who led all of the theoretical work and has been heavily involved in the experimental work. The experimental work that I mentioned at the end was led by Ronan Crosley. And I should also acknowledge collaboration with Sarang Gopalakrishnan, who will be here later in the week, and Surya Ganguly. And I'll put up here a summary of the things I talked about and some things I didn't talk about in case people want to ask questions about that. So thank you for your attention.